My digital pathology trailblazers, we are gonna be talking about ethical and bias considerations in AI and machine learning.
Learn about the newest digital pathology trends in science and industry, meet the most interesting people in the niche, and gain insights relevant to your own projects. Here is where pathology meets computer science. You are listening to the Digital Pathology Podcast with your host, Dr. Alexandra Zhurov.
Let's dive into the topic of our conversation today. Yes, biased. We are biased creatures. So what does that mean? It means that we have to be aware of that and mitigate it. And so we are here. Number 6. I can't believe we're already at number 6. Only number 7 to go. We are at ethical and bias considerations of AI and machine learning. So, yeah, medical practitioners and especially pathology, laboratory medicine professional in our case, but also imaging specialists, radiology, I would put them in the same category. And basically everybody who generates medical data in this paper, they call them data stewards. And I like this term very much because we play a pivotal role in guiding the ethical development and deployment of current and future AI ML technologies and machine learning technologies. What does that mean for us? How can we be good data stewards? Well, we need to know enough about this. We need to know enough about how it's being developed, what is being done. Basically, we need to know enough about this whole AI revolution, I would call it, to be able to be good data stewards. So that's what we're doing right now. We're learning about it. And we're going to learn about what can cause the bias. And obviously, they have fantastic tables and fantastic drawings. So we're going to focus on that. Yeah. So ethical principles in healthcare and medical research with extensions to medical artificial intelligence. So this is important. So I gave a presentation. I'm going to link to it after I publish in the cards, where I explained in general, like different ethical principles and where they come from, how they are defined. And some of these things are mentioned in this paper and obviously referenced. But if you want to do like a step back before diving into what they have here for AI, that's going to be the presentation. But basically, we have in this table, we have the ethical principle for healthcare and medical research, because this is very well defined. And then now we have a category for medical AI. So the first principle would be respect for autonomy, the principle of self-governance, which in case of healthcare and medical research is basically the individual's right to make their own decisions regarding their healthcare and participation in research. Do they want that? Do they not want that? And this is usually covered by informed consent. There's a little bit more about it later. And for AI, and here in AI, we have both developers and users. So not only the developers that are making those AIs, also the users must ensure that individuals have sufficient control over their interactions with AI. And there are different regulations, more than I even knew there were. Then the other principle is called, so this one is respect for autonomy, beneficence. Basically, the principle of doing good, because we also have the non-maleficence in a second. So we must benefit the individual, both as a healthcare professional and a researcher, and also AI developers and users are supposed to do that. They're supposed to maximize human benefits with those tools. Then we have non-maleficence. So not only are they supposed to do good, they have to do a lot of good, because enough, and also do no harm. So AI developers and users are responsible for preventing harm and mitigating risks. And then we also need to think about justice, the principle of fairness. So for physicians and researchers, it's that the treatment of individuals is fair and equitable, regardless of factors such as race, gender, socioeconomic status, and medical condition. And AI developers need to work on that as well, promoting equity regardless of factors such as race, gender, socioeconomic status, or medical condition. And it always, these things, okay, let's go to accountability, and then I will tell you a little story or a little thing that comes to my mind when I read this statement about factors such as race, gender, socioeconomic status, and all that. So accountability, we need to be responsible for our activities. So the doctor is physicians, researchers responsible for what they're doing, and also AI developers and the users, but they're accountable for ensuring that AI is designed, implemented, and operated ethically, transparently, and reliably. And so this justice, and it's not funny, but I always think about how it evolved. So I recently had my citizenship interview for becoming a US citizen. And one of the questions that they ask you there is, what is about amendments to the Constitution? And they ask you about one of the amendments about voting, like what is who can vote. And the most recent one is everybody who is a US citizen over 18 can vote. And the evolution towards that step was white males could vote, then all males could vote, and then females could vote, and now everybody over 18 can vote. So yeah, that's about justice and how it evolved in the US Constitution. Moving on. Okay. So we now know the rules, the principles. So we have the principles. These are our ethical principles: respect for autonomy, beneficence, non-maleficence, justice, and accountability. And where can this bias come from? From us who are creating AI, because we are biased creatures and we create biased tools, and we have to figure out how to make them less biased, so how to make them evolve like the US Constitution did. So let's look at this table about where the bias can come from. So we have the type of bias here in the left column, type of bias, what the descriptions and examples of in pathology. Some are very specific, some are less specific, but obviously data bias. This one is pretty self-explanatory. That's always super nice when I hear from you in real time. So data bias is basically if we have biased data. What does that mean, biased data? We have underrepresentation, overrepresentation, or misrepresentation in our case of pathology cases. And for example, if in pathology would be overrepresentation of certain demographics in diagnostic data sets. How can this happen? Like you work with one institution and they have data from one institution. And that's already biased data. So how do you overcome? You try to have your data sets as diverse as from different places as possible. Then we have algorithmic bias. This is a bias introduced during algorithm design, affecting diagnostic accuracy or treatment recommendations. And for example, in pathology, skewed prioritization of symptoms or conditions in diagnostic algorithms. So this can happen by design or not by design. And by design, I mean, if you prioritize the correct one, then it's okay. But, then there is always potential, like, how do you know that these are correct ones? But in many diagnostic algorithms, you give a weight to a certain symptom. So if there is something of a certain relevance, then you upvote it, give it a higher weight. So this can also happen unconsciously in a biased way that's going to give prioritization to stuff that maybe should not get the priority it should get. Then sampling bias. Well, when we have non-random sampling methods, then we can have skewed conclusions. For example, in pathology, that would be insufficient gross dissection for mapping of tumor bed to predict response to therapy. Interesting, this one. So for example, if we don't have the tumor dissected, so maybe then we have less percentage of tumor in the sample. I don't know, but basically this sampling bias can already introduce a problem. Then we have measurement bias. Measurement bias are inaccuracies in diagnostic tests or imaging technologies affecting treatment decisions. And here for pathology, it's going to be variation in test sensitivity or reference ranges across demographic groups. Then we have labeling bias. And misassigned labels of classification influencing disease prediction models. And that's pretty, let's call it close to my heart in the development of image analysis algorithms for pathology, because often you rely on annotations. Now we have models that don't do, they have self-supervision and work in different ways. But historically, it was a lot of annotations by pathologists, and they annotate in a different way. So you basically introduce subjectivity at the stage of labeling your data, and or like, you can mismatch reports to samples. There is potential for error, potential for bias, but mostly subjective interpretation of biopsy tumor grading results. This is an easy thing to introduce bias in. Prejudice bias from preconceived notions about certain disease or patient groups influencing pathology diagnosis. Then we have stereotypical assumptions about patient demographic influencing diagnosis or management decisions. There are, I'm not going to mention different diseases, but you can think of diseases that make you think of a certain prejudice towards the person that carries that disease. And, you have to realize that and then counter that. Then, environmental bias. Bias from environmental factors affecting disease prevalence or diagnostic outcomes in certain regions. What can influence disease prevalence? This is so cool, because I was thinking, maybe because environmental bias, right? Something that happened in the environment, like the Chernobyl catastrophe. But it's a lot less dramatic than that, because you can basically have different patterns in patient testing in academic hospitals in urban regions compared to community practices in rural settings. So when you test in a different way, or more frequently, less frequently, then you will have different prevalences of disease based on the environment that this person lives in. It doesn't have to be environmental catastrophe like the Chernobyl catastrophe. It can just be a big hospital versus community hospital. Then interaction bias. Interactions between different diseases or comorbid conditions affecting diagnosis. I'm like, interaction bias? Like how you interact with patient or how you interact with AI? No, how diseases interact with each other. And in pathology, an example is going to be serum antibody chemistry interferences in patients with similar disease influencing test results. So yeah, basically comorbidities and, elderly patients, they have multiple disease, not only many people have multiple disease and they interact with each other, and you have to be conscious of that bias. Something interesting is feedback loop bias. This is a bias exacerbated by diagnostic feedback loops where historical data or previous diagnosis influence future diagnostic decisions. So this is so easy to happen. This was there before, so it has to be continuation of the same thing, right? It can be both in treatment diagnostic settings and also in research settings, where you have groups of animals or groups of research subjects. In my case, it's going to be animals because I'm a veterinary pathologist. But then you see something in one group and I'm like, okay, then it must be a different variation of the same thing. Doesn't have to be. And that's already, your feedback loop bias in action. And an example is predicting future ancillary studies based on initial diagnosis without supportive evidence, right? You don't have the evidence for this new conclusion. You just have the historical thing. It's like acting according to the best predictor of future behavior is past behavior. And maybe in psychology this tracks, but in medicine and research, you should have some data backing it up. Representation bias. Bias from inadequate representation of diverse populations in diagnostic data sets affecting accuracy. So that was a little bit connected to this data bias. And you have underrepresentation of minority populations in genetic screening databases. It's funny when I read that, because underrepresentation of minority populations, they're going to be underrepresented because they are minority. But then it's like a vicious circle. Because they're minority, they're going to be underrepresented. Anyway, there's less of them because they're minority, and then you don't like actively reach out or find this data to have the representation at least to the level that it's actually represented in the population. And temporal bias, this is something like some of these I have no idea how you should overcome, or you even can overcome. You just have to like monitor and be super conscious about it. So the temporal bias is due to changes in disease prevalence or diagnostic criteria not reflected in historical diagnostic data. And something that can happen in pathology is evolution of disease classification, leading to discrepancies in historical and current diagnosis. And I think this is currently happening for cervical cancer screening and also maybe urinary bladder cytology. It's happening as we speak, and the historical data is not going to match the current data because the scoring criteria changed. Also, like probably IHC scoring criteria for different markers, including HER2 and others. Anyway, that's something that I don't know how to overcome. Maybe you need to like have a time cut point and say a different algorithm for before that cutoff when the criteria changed, and a different one after. Okay, transfer bias. Bias from differences between diagnostic practices in training hospitals and those in community settings. We had something similar here, the environmental bias. And yeah, we have variations in diagnostic criteria between academic and community healthcare centers. So here's variation in diagnostic criteria. There, it was basically different patterns of testing, but kind of connected. And then confirmation bias. Initial beliefs or diagnostic decisions influence subsequent interpretations or actions. This is also another thing that we have hardwired in our brain. Shortcuts based on something that we already know. We extrapolate other information. And then pathology example, favoring evidence that confirms initial diagnosis or treatment plans without considering contradictory information. So we always have to check ourselves. Check your bias. There's a lot of biases to check. So very important in the context of medicine research AI. And let's look at this figure where we have a list of guidelines that actually can be used. So one, not argument, but something that, a statement that people say, like, where are the guidelines, the regulatory agencies, they are lagging behind. How do we do it? Well, there is a lot of guidelines that I didn't know existed, but now I know, and you will know as well. So these guidelines are for respective stages of AI in the medical life cycle. And we're looking here at the medical life cycle. So what is this medical life cycle? We have the research and development at the beginning of the life cycle. Then we have clinical implementation at the end, and the parts where we are very active as researchers, as clinicians, physicians, pathologists. For me, it's going to be preclinical development. Then we have clinical trials and clinical translation. And in the preclinical development, we have basically everything before we can introduce something. In my case, it's going to be a compound, a candidate drug into the clinical trial. It can be a diagnostic test, AI test, whatever, right? So we recognize the need, we harvest data, we ensure explainability, and then think about copyright and IP considerations. And at the bottom here is the AI. So we recognize the need, then we select the AI technique. And we harvest the data. I love this little picture of harvesting the data. Let me show it to you. Look at this data, a tree with data, and a person is harvesting the data. So we harvest the data and then develop and validate the algorithm. And when we develop and validate the algorithm, we have a bunch of guidelines that we can use. We have QUADAS-AI, starred AI, robust AI, tripod AI, and there is another table. I'm not going to be going through these guidelines today, but I just wanted to let you know when you are at this stage of develop and validate algorithm, you need to check these guidelines. People already thought about it. You don't have to reinvent the wheel. You don't have to start from scratch. Look at these guidelines and use them. I think it's always super, super useful to basically leverage other people's research, and that's supposed to be the point of research, right? So that we can do new research. So we can do the same for guidelines for AI. Then what have we done? We have developed, we ensured the explainability, and then we published our research, checked the copyright here, and we now developed a product and integrated with digital systems. Oh my goodness, if we're here, we're really, really advanced. But then we need to go to clinical trials. So we go and we have another set of guidelines for different phases of the clinical trials. Let me make it bigger for you again. So phase 1, 2, early, we can use the Decide AI. Decide AI. Phase 3, clinical, we can do Spirit AI and Consort-AI. So we already have different guidelines. And then when we are the luckiest of all and also the best researchers of all, we go into the clinical implementation, clinical translation, and then we deal with regulatory agencies, right? So we have regulatory inspection and approval. We analyze the health economics. We release to market and then adopt, scale, and check if there is a return on investment. And we have the system health surveillance and updates. This last part is already with authorities, with regulators, before we have guidelines that we can apply. And obviously the regulators and authorities have their own guidelines. And if you don't meet the criteria that they have, then they're not going to be even talking to you. But the point of this is to show you that there is guidelines that you can. FDA also has recent regulations for developing and validating algorithms, both for preclinical work, for clinical work. On the preclinical side, it's very much risk assessment based, so very not catering, but addressing the principle of beneficence and non-maleficence. So if the benefits have to very much outweigh the risks, and also explainability and different things. So they are crafting those guidelines according to the principles that we are learning about in this paper series. So let's see how something can become biased. Well, we see that it's not too difficult to bias something because we have so many different sources of bias. But here is the representative example of bias introduced in developing an AI algorithm for prostate cancer. And so here in this image, you have this hypothetical distribution of prostate cancer Gleason score by hereditary population groups. And we have Eurasian and North American populations. And we have the prevalence of the different Gleason grades. And we can see that 1, 2, 3, 4 is very low prevalence, right? And we use this data for training. And then we have biased distribution of training data, right? Where our Gleason 5 is very low. And our AI robot gets this and applies this to diverse patients, whereas the training data was not from diverse, not geographically diverse. And then it says positive for populations with low Gleason grade 5 tumor prevalence and negative for populations with high prevalence of Gleason grade 5 tumors, right? So we have positive in the areas where the data was taken from and negative in the areas where there was no data. But if we use data from South American, African, and Oceania populations as well, which we can see that their Gleason grade 5 prevalence is a lot higher than in the previous data. And we combine the data sets. So we have both the North American and the rest of the world, South American, African, and Oceania. We have a different distribution of training data, unbiased, representative. And then we can see that actually this prediction of prostate cancer outcome is positive for all populations. Yeah, this is easy to produce this type of bias because access to data is difficult. Like, how are you going to get data from all over the world? It's difficult. But nevertheless, if you want an unbiased algorithm, then you need to do that. Unbiased generalizable algorithm. If you cannot do that, then you cannot apply this algorithm to those populations that were not represented in your data. And this is what the authors and I mean by check your bias. Where can you be biased here? So, okay, we checked. There's a lot of sources of bias. How do you mitigate this bias? What is the bias mitigation? When I was going through this part, it basically is like check for it and figure out how to like not have it. Once you realize it's there, then you know what to do to counter it. In general, in digital pathology, it's already a multidisciplinary field where you have everybody involved in the care actually working on this, IT, lab professionals, pathologists, obviously, but then clinicians or treating physicians getting the data from digital pathology. Also, like other specialties like dermatologists showing slides to their patients that were generated by digital pathology. And then next level is AI, because now we have developers, now we have computer scientists, engineers in that group. So definitely, and statisticians, like everybody who is involved in research. Let's go back to our bias mitigation. Well, what can we do better when we collect data and prepare data? We gather diverse data sets. So it's funny because once you realize, okay, this is a bias and I have to counter that bias, it's pretty self-explanatory how to counter a bias where you don't have diverse data sets. Well, you get diverse data sets, right? Easy. But realizing that you don't have diverse data sets, or that you're applying a solution built on non-diverse data sets to diverse populations, this is where like you have to do the check. So here you actively seek out and include diverse data sets that represent different demographics, geographic locations, and socioeconomic backgrounds. This is crucial. And here I always say about different initiatives, because access to data is difficult. When you have a collaboration with someone, you like want to maximize that collaboration with a healthcare institution. And then, okay, this is the population from the institution. So here I mentioned two organizations. One is the Digital Diagnostics, not organization. What is this? Foundation, Digital Diagnostics Foundation, started by Matt Levitt. And that is basically his goal. He gathers data from diverse populations, pathology, radiology, all the medical data. And whoever wants to get access to this data then works with the foundation, both on the data providers, so healthcare institutions and patients, and the data users, meaning the institutions that want to develop tools or use this data. And they are supposed to be, or their role is to be an honest broker in the handling of this data. And another initiative that is happening actually in January next year, they will have their annual meeting in Berlin, Germany, where I studied. So maybe I did my PhD and my residency. So maybe I should go there and do a live streaming from this event. And that event is the annual meeting of the Big Picture Consortium. This is a private-public consortium in Europe. And the role of this consortium is aggregate data, not only from diverse countries, diverse places in Europe, but also from different stages of the medical life cycle. So both preclinical and clinical, and they have like a huge data base that they're going to be building. So, but this is too institutions that I talk about. There is another option to use federated learning, swarm learning, different decentralized learning techniques, topic for another presentation, and also topic of different videos. And I'm pointing up because I want to later link to it so that you can have a look at it later or put it in the show notes. When I'm pointing down, it's show notes. When I'm pointing up, it's card on YouTube. Anyway, so we do that. Then model development and model development and training. We select appropriate algorithms and features. This is important. Then conduct evaluation across different demographic groups to identify any disparate impacts. And techniques such as fairness-aware learning and bias detection algorithms can help. Bias detection algorithms. So these are automated techniques, ways of introducing these checks into the models. Model evaluation, performance evaluation across spectrum of demographics and diagnostic groups, and it should be more than traditional accuracy metrics and include bias and fairness assessment. So evaluating the model's performance, for example, across patient populations, diagnostic categories, staining protocols, reference ranges, etc. So there was one publication that we actually talked about in one of the digital pathology digests, where there was an algorithm that you could apply to your algorithm or to your data. To your data to show like a performance checker. I think maybe bias checker, where you run an AI algorithm on data, and this other algorithm is showing you on which data it didn't really perform because the data was out of distribution compared to the training data of the algorithm you were checking. I know it's a convoluted explanation, but basically it shows you the subset of the data that your algorithm that you're evaluating is working well. You can use it there. And then it tells you the rest, no, don't use this algorithm on the rest of the data. So what do you use? What do you do with the rest of the data? And the rest of the data is going to be images from patients, right? You maybe send them back to the pathologist, or you maybe use a different algorithm that's more optimized for, a specific demographic, a specific presentation of a tumor and things like that. So there is a lot of research going on this. Model deployment and ongoing monitoring. Regular bias assessments throughout the AI model lifecycle helps identify and mitigate biases as they arise, including pre-processing steps, algorithmic adjustments, and post-deployment monitoring. So basically, a little bit of a never-ending story. You need to monitor, you need to check. And there is also interpretability and accountability. And here, concepts like explainability and self-reflection come into play. Self-reflection, for example, self-reflection, introspection, specifically allows AI models to analyze their own decision-making processes by identifying the biases and factors that influence their outcomes. So this concept was new to me. I didn't know there was a way to flag biases with an AI, right? And explainability is the I would call it branch of AI science that ensures that AI decisions are understandable to stakeholders and end users by providing clear justifications of their predictions, outputs, and actions. Yeah, and words of wisdom here: effective bias mitigation requires a holistic approach. Really? Yes. Now, after listening to me for 42 minutes, you know that it's not one fix fixes all, like in life, right? Holistic approach at multiple stages of development, and something that guides everything here are the FAIR principles. So FAIR principles regarding data, they refer to findability, accessibility, interoperability, and reusability principles. Is our data always fair? No. There's a fantastic graphic for this as well. So what does that mean that it's findable. The data is findable. Like I always think, let's think about annotations. Are they reusable? No, they disappear in your algorithm and then you never see them again. Hundreds or thousands of pathologists' hours of work. But let's start with findability. Let me do this highlighter. Findability. Data is assigned a globally unique and persistent identifier. I don't know. When I go through this FAIR principles, I'm thinking we're not that fair when it comes to data. But let's just go through it, right? Data is described with rich metadata. How often do we miss metadata? Probably often. Data is registered and indexed in searchable resource. Like really? In present for a lot of data that I am thinking of. Searchable. Like only recently have we come up with ideas, and I saw some of these at USCAP, to search images, right? Not only based by metadata, but also by image. And image data is a super important part of pathology data. It's like crucial part, right? Metadata specify the data identifier. Okay. But now let's stop complaining about how little of this is actually available. Let's use these principles and make more of it available. So that was findability. This is the F from FAIR. Accessibility, that's the A. Data and metadata are retrievable by their identifier using a standard communications protocol. The protocol is open, free, and universally implementable. Authentication and authorization procedures, when necessary, are clearly outlined, and metadata remain accessible even when the data are no longer available. That is interesting. See, even when there is no more data, there is metadata. So the open padlock is the symbol. Interoperability, the I from FAIR. Data use a formal, accessible, shared, and broadly applicable language for knowledge representation. Data use vocabularies that follow FAIR principles. Data include qualified references to other data. And then we have reusability. That was my rant on annotations. Data and metadata are well documented and richly described with accurate and relevant attributes. Data are released with a clear and accessible data usage license. And here I want to give a shout out to the authors and to Modern Pathology, because we have a license that allows us to use these papers for activities like what we are doing right now. Data sources are shared. Data are shared alongside methodologies and research results. So these are the FAIR principles that we should adhere to when we generate data and when we build stuff from this data. Oh, and here we're going back to the guidelines that can guide you when you develop some AI algorithms. Let me show you the original image that we were discussing, this one. So these QUADAS, STRAT, and all these different guidelines, there is a special table at the end of this paper, and it gives you the list of those guidelines: START-AI, Tripod-AI, Probust-AI. It tells you what is the purpose. So for example, for START-AI, reporting standards for studies, evaluating diagnostic AI algorithms, ensure transparency. Then when are you supposed to do it? Evaluation before diagnosis, and how it corresponds to the FAIR principles. So how I would approach it when I'm doing something, I would go to let's assume I'm an AI developer, which I'm not, I'm a veterinary pathologist, or somebody who manages the development of these algorithms. When we develop and validate, then we have QUADAS, START, Probust, and Tripod. And we go to the table and we check, okay, do these apply to us? How do they relate to the FAIR principles? When do we do? Tripod is for development of diagnostic tools. And then Probust is development of diagnostic and prognostic tools. So wherever, right? And then we have a lot more of them, a full table. Let me just tell you the timelines when we're going to be using them. Development and validation of AI algorithms, reporting of AI studies, development and validation of AI models, integration into clinical decision-making, clinical trial protocol. So this one is important specifically for people working with clinical trials. Reporting of AI. So like there's one for clinical trials and there's one for reporting clinical trials. Spirit is for clinical trial protocol. And then CONSORT-AI is reporting of AI clinical trials. And then QUADAS-AI is reporting of AI studies. So we have a lot of them and we can use them. So let me know let me know what's new from this, because some stuff was not new for me, but these guidelines were new for sure. The fairness principle, I knew about it, but it kind of, I learned about it and it was like in the background and not really at the forefront. It should be at the forefront. Thank you so much for joining me today. If you are interested in learning more about digital pathology in general and AI, there is a course that I have for AI. This is the Pathology AI Makeover. And if you're just starting, then grab the book, Digital Pathology 101 book. You can grab a free PDF from the website with the QR code that you're seeing on the screen right now and start your digital pathology journey. And once we are done with the series, the AI section is going to be updated. So if you have the free PDF, you already downloaded. So even if you did it like 2 years ago when I first published this book in 2023, you are on my list that will get the updated version. So if you don't have any version yet, get whichever, even if it's not updated yet. And then when the new one is out, you are going to get a free PDF. Thank you so much for joining me, and I talk to you in the next episode.